Hey everyone, welcome back to Engineering Illustrated. Today we'll be discussing vector addition, specifically what it looks like to add two vectors. Now it's usually pretty clear what it means to add two numbers, but it can be confusing to think about adding vectors. Fortunately, there are some similarities between adding a normal number, which we call a scalar quantity in engineering, and adding vectors. First, let's think back to the first time you learned about addition. It probably went something like this. If Johnny has 5 apples and he gets 3 more, how many apples does Johnny have now? Obviously, he has 8 apples. Another way to visualize this is on a number line. Convention says that the right side is the positive numbers and the left side is negative, so let's stick with that. In our little example, we start with 5 apples, so let's go to 5 on the number line. We got 3 more, which is positive, so we're going to move to the right 3. Which leaves us with 8, which is the same answer we got before. Obviously, this is a simple example, but it can still help us visualize how vectors add up. Now this is a one-dimensional problem. The only variable is the number of apples, and you can either gain or lose them. Vectors are similar, but they work in higher dimensions. Let's take a look at the similarities with 2D vector addition. A two-dimensional space can be set up by placing two number lines at right angles to each other, intersecting at 0. Adding a grid can help us visualize the space. Vectors have two pieces, a direction and a magnitude, which may sound familiar. An intuitive way to visualize them is with an arrow. The arrowhead points in the direction, and the length of the tail is the magnitude. This is how vectors are drawn. The most convenient way to write a vector is usually in Cartesian form, because it gives you the x and the y components directly. A Cartesian vector looks something like this. Vector v equals vx I hat plus vy j hat, where vx is the x component of v and vy is the y component. I hat and j hat represent unit vectors along the x and y axes, which is good, but it can make things look a bit messy. So I prefer to write my Cartesian vectors as an ordered pair like this. The first number tells us how far we go in the x direction, and the second tells us how far we go in the y direction. Let's do an example. If we have vector v1 equals 5, 3, we need to go 5 steps in the x direction, which is to the right, and 3 steps in the y direction, which is up, starting at the origin. The vector is formed by drawing an arrow from the starting point to the ending point, like this. Now say we want to add vector v2 to v1. Just like with the apples, all we do is start with what we have and go where the second vector tells us. Earlier we had 5 apples and we got 3 more, so we moved to the right 3. Vectors are the same, only this time 2 directions or components are involved, instead of just the number of apples. This time we'll start with v1, and then from the head of v1 we will go where v2 tells us, 1 to the right and 4 up. Once we've drawn that vector, we can draw the resultant vector by starting where the first vector started, which is at the origin, and drawing an arrow to where the second vector ended, as shown in purple. The head of the purple resultant vector gives us the sum of v1 and v2 as 6, 7. Along with understanding visually what is happening, it's also important to be able to crunch the numbers without needing to draw a picture every single time. Luckily, vector addition in Cartesian form is super easy to do this. Simply add the x components, and then add the y components, and put it back in the same format as before, and that's it, you're done. Adding the components like this might make you wonder if the order of vector addition matters, and even if you weren't wondering, I'll tell you. The order of vector addition does not matter, it's commutative. Look what happens if we start v2 at the origin, and then put v1 after it. We end up at the same point. This is super convenient because it's one less thing to keep track of. Drawn like this, the two vectors can form a parallelogram. This is called the parallelogram law, which basically means you can make a parallelogram out of any two vectors and the resultant will always be the diagonal. It's occasionally helpful to know this, but it's usually not critical. The actual definition of the parallelogram law is in the description if you're interested in that. The more useful method of visually adding vectors is usually the triangle construction method that we showed earlier. Another note is vector subtraction is the exact same process, but you flip the signs of the vector you want to subtract. Visually, that means you put the head of the arrow on the other end and do the same process you would for addition. It would look something like this. Let's recap what we've learned with a super quick example. Vector addition is very simple when we know the Cartesian components. To draw a picture of vector addition, first, draw the first vector with a tail at the origin. Second, draw the second vector with the tail connected to the head of the first vector. And third, complete the triangle by connecting the tail of the first vector to the head of the second vector. And finally, find the values of the resultant vector by summing the x and y components individually. Or, if it's easier, you can just get the answer graphically. And then the note to remember, subtraction is simply addition of a negative vector. We multiply the vector we want to subtract by -1 and add it just like normal. Thanks for watching. Hopefully this was helpful. Let me know down in the comments if there's any content you'd like to see, or if there's any topics in engineering that are particularly difficult for you to understand. I'll see what I can do about explaining them. Thanks, and we'll see you next time.